Of all the planets in our solar system, there's little doubt in saying that Mars has attracted the most optimism about the possibilities for extraterrestrial life. And it reaches right back to Percival Lowell and his speculations about Martian canals. He drew detailed maps of Martian canals that he thought had been constructed by ancient Martian civilizations seeking to channel water from the polar ice caps down to the equator to their beleaguered, desiccated cities. But Mars has also permeated science fiction, stories of warring Martians appearing from Mars to try and lay claim to the Earth in H.G. Wells' War of the Worlds, for instance. And even in recent times, the possibility of civilizations on Mars has captured the human imagination. Here's a rather nice example. On the left-hand side, you can see a hill that was photographed by the Viking orbiters in the mid-1970s. The hill has a distinctly monkey-like appearance, some sort of primitive primate. And those people who saw this image in the 1970s began to believe that it was some monument constructed by a Martian civilization. Well, when you take this photograph again with higher resolution images taken by Martian orbiters that you can see on the right-hand side, you can see there is no monkey face on Mars. This is just a hill, a mesa, an outcrop of rock that really has no resemblance to a face at all. This is just a trick of the low-resolution imagery with which this hill was photographed in the early 1970s. It's a very good example of how, if you stare long enough at an image, you can see what you want to see. Percival Lowell stared at the surface of Mars through his telescope and he saw what he thought were canals, an optical processing trick of the human brain as it tries to create lines between images that it's trying to connect. He saw features on Mars, his brain created lines between them, and he thought they were canals. In this way, people look at images on the surface of Mars from orbiters and they think they see monkey faces, whereas in fact when we look at them at higher resolution, we see that there are no images of faces at all. Here's another example. This is an impact crater on the surface of Mars. Is it a monument built by a happy Martian civilization? No. It's just an impact crater, but if we look at it in particular ways, we can see all sorts of things in these images. These are lessons from the history of astrobiology, lessons about how one should be cautious about gathering data, but also cautious about making interpretations on things that one might want to believe. One might want to believe that there's life on Mars, even though the data is telling you something very different. The first attempt to seek life on Mars using a real experiment were the Viking biology experiments. These were launched to the surface of Mars on the Viking landers that landed on Mars in 1976. The Viking biology experiment consisted of 3 sub-experiments, and these 3 experiments were the following. First of all, there was a labeled release experiment, and here nutrients were placed into the soil that had radio-labeled carbon. The idea is that the nutrients would be used by microbes that would produce waste products, and these waste products would contain radioactive carbon, such as carbon dioxide, which could be picked up by the instrument as a demonstration that there were metabolically active microbes in Martian soil. The second experiment was the gas exchange experiment, and here nutrients were added to the soil to see if any gases were given off that might be the products of biological activity, such as methane, hydrogen or oxygen, that might demonstrate that microbes were actively using those nutrients and producing gases as a waste product. And the third experiment was the pyrolytic release experiment. And here carbon dioxide with radio-labeled carbon was added to the soil. The idea is that the carbon dioxide would be taken up by autotrophs, microbes that use carbon dioxide as a source of carbon. This radio-labeled carbon would be incorporated into the cells, and then the cells would essentially be heated up, burnt up inside the experimental apparatus, and this radioactive material, radioactive carbon that had been fixed in the cells by the cells taking up the carbon dioxide, would be released and detected. The experiment also had a heat sterilized control, where Martian soil was collected by the Viking lander and heated to kill any possible biology, and then the same experiments were performed on this heat sterilized control. So what were the results of the Viking biology experiments? Well, the labeled release experiment did give off gas, but this was not repeated in later attempts at the same experiment, so that was inconclusive. The gas exchange experiment did result in the production of oxygen, but the problem was that oxygen was also produced in the non-biological control that had been heated to kill any potential microorganisms. And then finally, in the paralytic release experiment, radioactive carbon was found in gases released in that experiment, but it was also found in the non-biological controls. Taken together, these results suggest that there was a reactive component to Martian soil. We now know that Martian soil contains perchlorate, an oxidizing compound, and it may contain other oxidants as well. And we think that those oxidants were reacting with the nutrients, other compounds added in the Viking experiments, and causing the release of these gases in the experiment. So it wasn't caused by biology, but rather by chemistry. This is consistent with what we now know about the Martian surface. It's a very extreme surface. There's no liquid water, there's high levels of ultraviolet radiation and ionizing radiation. It's not a very good place for biology, and so we might expect that the Viking biology experiments would be inconclusive in the discovery of biology, but might suggest the possibility of reactive soils. Since the Viking experiments, there have been other papers that have brought evidence suggesting life on Mars, and perhaps the most famous one was a paper published in 1996 in Science magazine about the discovery of potential life in ancient Martian meteorites. And the meteorite at the focus of these studies is ALH 84001, a Martian meteorite launched from Mars many millions of years ago and discovered in Antarctica. It sat in Antarctica for over 13,000 years and then was discovered by scientists. We know it's a Martian meteorite because its composition matches up with the composition of the Martian surface, and it contains within it bubbles of Martian atmosphere trapped within the meteorite that have the same composition, chemical and isotopic, with the Martian atmosphere. What did scientists find in this meteorite that led them to suggest the possibility of life? Well, first of all, they found shapes that they claim look like microorganisms, long tubular-like structures on the surfaces inside the meteorite. The scientists also found magnetite in the meteorites. Now, magnetite can be produced by non-biological processes, but it's also produced by bacteria, magnetotactic bacteria, that use little grains of magnetite to align themselves with magnetic fields. And one of the characteristics of these bacteria is they produce chains of magnetite, and chains of magnetite were claimed to be found in the meteorites. The scientists also found PAHs, polyaromatic hydrocarbons. These are complex organic compounds that could be associated with life. They were found inside the meteorite and associated with globules of carbonate rocks carbonate minerals inside the meteorite. The scientists claim that the association of these PAHs with the carbonate granules suggests the possibility that these came from life rather than from contamination outside the meteorite. Each one of these lines of evidence is contestable. Shapes of microbes may not be real microbes. They could be non-biological processes depositing filamentous-like minerals on the surfaces of meteorites. Chains of magnetite could just be chains of magnetite minerals formed in non-biological reactions. And of course, organic compounds such as PAHs we know are formed in the interstellar medium. They're not necessarily associated with biology. But the authors claim that each line of evidence, when put together, suggests the presence of biology, even if individually they can be contested. The question remains open. Is this evidence of early life on Mars? Astrobiologists debate this evidence vigorously. Another problem greatly debated amongst biologists is whether the shapes of microbes found in these meteorites are too small to be microbes. They're much smaller than typical microbes found on the Earth. Maybe they're even too small to be biological entities. These are also questions that astrobiologists are attempting to address. So what have we learned? We've learned that Mars has always been a focus in the search for life. We've learned that the first serious experiments sent there were the Viking biology experiments. The Viking experiments can be explained by non-biological processes, but more recent evidence has come from Martian meteorites. But even this remains highly controversial. Really, the question of life on Mars can now only be solved with robotic and human explorers and by studying new samples of the surface and subsurface of Mars to get more evidence, more data points that might help us to understand whether Mars was ever habitable and whether it ever harboured life.